let me invite Matthias, the Managing Director of OxFA, to the stage.
So, good afternoon, everybody. My name is Matthias. I'm Managing Director of OxFA GmbH, and for years now, we all agree on the fact that one thing is that biomass is the key to more or less completely defossilize our chemical industry. And why is it not working at scale at the moment or right now is that the feedstock, in our perspective and for our system we are looking at, was never the problem. The problem might also lie in the chemistry. And within the next 10 minutes, I would like to show you how we, as OxFA, tackled that entire system. So let's start with the numbers. Those are numbers who you're all aware of. Over the year, we turn over 15 to 17 gigatons of fossil carbon, of which 10% goes into material use, what we are all talking about, to replace it with bio-innovation technology. The good news is 2 to 5 gigatons per year are already sitting in unused biomass potential. So that means we as an industry have already solved the feedstock problem. But the question that is arising is, have we solved the chemistry problem? And we focused on 3 barriers we came across with many technologies we had a look at. And we'd like to argue that those 3 barriers, first, feedstock variability, where classical biorefineries often struggle with heterogeneous biomass streams, which leads to unclear processes and not really good product stability. Low selectivity, this is due to the fact that if you have a complex biomass and want to get with a complex biomass directly into your product, you often end up with mixed products where you have high separation costs and sometimes a poor energy efficiency and low carbon efficiency. And last but not least, the infrastructural gap, which means that novel bioprocesses struggle with plugging directly into the chemical infrastructure. And this is due to then with high capex hurdles, and the scalability is more or less challenging. So please keep in mind those 3 barriers. I will address them later on. So here is our core idea we developed. And it's almost a little counterintuitive, because when you try to build complex and high-value products out of lignin, cellulose, and so on, you often end up with different products. We see that we want to try to have those cellulose, hemicellulose, lignin, and get this from sugars over wood to residues, the entire value chain, with, depending on the substrate, with a carbon efficiency from 50 to 80% to exactly 1 molecule. And that 1 molecule for us is formic acid. It's a stable, safe, and transportable fluid, and it's 1 carbon. So more or less we are mimicking the entire story which conventional chemical industry is doing already. They take syngas, they take methane or oil, break it down to syngas, and from that on they build up. And this is something we also do. We break down first, build then, having our C1 platform with the formic acid. This is so the platform already having a 1 million ton market in feed preservation, leather tanning, textile industry. But this platform for us is not the endpoint. In this case, it's our lever. So from the formic acid itself, we then build back up to methanol, which has already a current market of 100 million tons. We go into hydrogen and CO, or into methyl formate. So now I want to show you how we actually do that and how it works. And here we come back to the 3 barriers I mentioned earlier. So in our system, feedstock variability and low selectivity are already solved. We take red 3 residues. In this example, it's crude glycerol from biodiesel production. Get this over a pre-treatment step into our core technology. which is the catalytic oxidation reaction. A flash step and a subsequent distillation leaves us with formic acid ready as a drop-in for already existing industries. And the reason why this works comes down to actually one point, and this is our catalyst. It's a polyoxymethylate, being a strong oxidant with a very high solubility in water. High solubility in water is beneficial in our case, as we more or less do it with biomass feedstock, where water is always contained. It's noble metal free, we produce it on our own, and due to the fact that it has a very high selectivity towards formic acid, here we defeat the struggle someone has with direct conversion into the products. So this is more or less the breaking down. Now we want to build this back up. And here we close the third barrier. It's the infrastructure gap. From formic acid, we go over methyl formate and then hydrogenate it to methanol. Not sure why this graphic is not really fine, but it really elegantly closes the entire system. So we have renewable electricity, which is making the electrolysis working. In the electrolysis, we get oxygen and hydrogen, and in our case, we use both. So we have the oxygen in the oxidation of the biomass to get to the formic acid, and we have the hydrogen to feed the hydrogenation step towards methanol. In the end, if methanol is then used in energy application, we have the CO2, which then directly feeds back into the biomass. And that is the momentum where our biomass process becomes a scalable molecule factory. We have in our system then drop-in formic acid and methanol for already established markets. And how do we do that? And did we really do that? So you see here a picture of our one step for the formic acid production. This is our production site. It runs. It has more than 6,000 hours time on stream, has a highly degree of automation, and equipped with an online NMR, we have real-time quality product analysis. We are producing roughly 1 to 3 kilograms of formic acid and 1 kilogram of methanol per hour. So this then goes into the right side of the graph. We have our biobased C1 platform chemical, which can then go into hydrogen, CO2 or CO, go into methyl formate, which has a already existing 6 million ton market. We can go into the methanol business. And if we look at the numbers there, the methanol market is intended to grow plus 400 million tons till then 2050. This is more or less due to the increase you might have for the maritime sector and for the sustainable aviation fuels. And then we have the C1 platform chemical to go to SAF, DME, light olefins, and this entire businesses. So we really have then this OxFA modular decentralized plants which make it possible to make feedstock into this C1 building block. So essentially the feedstock is ready and the catalysis is ready. The question is, are we really ready to integrate it? And we have, from our side, a new competitive production route for sustainable formic acid. And we are really seeking for strategic partners, for drop-in customers in existing markets concerning formic acid and methanol. It's a really tough one, because if you think of, and we had the example of UPM in Leuna, right next to the UPM Biomag site, there is sitting a plant from Total Energies, which is currently producing 700,000 tons of methanol based on methane. So more or less means we are competing in a really developed market with depreciated plants, and the decentralized system will ever follow a complete different way. And therefore, we are seeking here a new way of thinking C1 chemistry, sustainable, innovative, and scalable. And with that, I want to give you your networking coffee pause and would be very happy to have discussions about our system there.